Hey guys, today we're going to be going over a Leetcode question. This question is currently being asked by Google, and the question is called N Queens. Let's get to it. The problem description is, the N Queens puzzle is the problem of placing N queens on an N by N chessboard such that no two queens attack each other. Given an integer N, return all distinct solutions to the N Queens puzzle. You may return the answer in any order. Each solution contains a distinct board configuration of the N Queens placement where Q and period both indicate a queen and an empty space, respectively. So for this example, where N equals 4, we have a size 4 board, and we'll have two configurations of how we can place this. And you can see each row is that arrangement of periods and Qs to explain where the Q is on the board. So first, for context, a queen can attack any other chess piece in three ways. It can attack across a row, down a column, and diagonal up or diagonal down. So consequently, we need to make sure that there's no queens being placed in the same row, the same column, or the same positive or negative diagonal. So the first approach that comes to my mind is, like, obviously we could place them in every single position, and like that would be a backtracking solution, but this would be like a crazy value for this. Like N equals 4 would be like 16 choose 4, which would just be like a super large and inefficient solution. So the first thing we can do to make this a little more intelligent is we already know that we can't place a queen in the same row. So consequently, the logic that I talked through, pretty similar to how we did Sudoku Solver, is moving left to right, top to bottom, if a move is valid. So if we can place a queen in that space without it being attacked, place it, and then after we place it, move to the next row and try to place the next row's queen. And then if this is impossible, return to the previous row and move that queen to the next spot, moving left to right. And then once we get to the very bottom, so once we have placed N queens, we know we have a valid board solution, so we can append that solution to our board. So let's talk through this with like this actual example of like the N equals 4 and see if this will hold up. So in this, I guess we're following this algo, moving left to right, top to bottom. We'll try to place the queen. That's valid because there's nothing in the row, column, or diagonal. So then we can hop to the next row. Can't place anything here because there's something in the row. Can't place it here in the diagonal, but we can place it here. We'll hop to the third row. Can't place anything here. Can't place anything here because the second row is diagonal. Can't place anything here, and can't place anything here. So now we'll go to this. If this is impossible, we'll return to the previous row and move that queen. So we're going to return false here, go up to this row, move the queen here, and then start again. So we can't put the queen here because in that column, but we can put the queen here. So we'll move to the last row, can't put it here, can't put it here because there's a queen in the third row, can't move it here because the queen in the third row is diagonal is this space, and we can't move it here. So we have the same problem again where we return to the previous row, move that queen, can't move it here because the diagonal, and can't move it here. So we'll again return to the previous row, and then again we're at the last column in the row, so we'll require that we move this queen. We move to the second row, and then here we can't put that queen there because there's a queen in the diagonal. Can't move it there, can't move it there because the diagonal, but we can move it there. We put a queen on the next row, and we can place it here. We move to the last row, can't place it here, can't place it here because of the column, but we can place it here, and we'll actually get the first correct configuration on the left side of example 1, and then we could do the same thing to eventually get the second configuration. But it looks like this will hold up. So before we code this, then let's talk about state, base cases, and choices, because that's what I always think about when I do a backtracking solution. So our state is that we will care about our current row and our current column. our base cases are that when our row equals n, we'll know we found a solution. So like number 3. So we can return true, append to board. And what this really means is we have placed n queens. And then our other base case is our column equals n. So we couldn't place this queen. So we're going to return false and then backtrack. And then our choices are we either place it, and then we go to the next row. So we'd like solve the next row plus 1 at the 0th column, or we just continue trying the next column. And like we can probably use some for loop, so that wouldn't actually be like a recursive call like this first choice would be. But the don't place it would just be like a continue rather than a recursive call. So then I think like we can really just code this up, and then we can like figure out how we're going to implement like is valid as we go. But the real business logic for is valid is just making sure that given a queen on a certain row and column, are there any other queens at that row, that column, or that one of those two diagonals? So let's code up these state base cases and choices. First, we're going to need a ret array. We're going to return the ret array, and then we're going to have a current board. And the current board is going to be period for I in range n, for j in range n. And then we're going to solve, have some solve function like we discussed in our choices. Def solve, we're going to have a row and a column because we want to keep track of our state. And then after, we should return ret. One point here is if we do append board to ret, the output requires that each row is a string, but right now it would be like a list of separate strings. So what we're going to need to do here is say that we're actually returning like the join of each row for row in board for board in ret, and this should work to actually like enumerate our like rows, which will look like this, to look like this. So let's implement solve now. So the logic here will just be our base cases and then like our choices. So our base case is if r equals n, we can return true. We found a solution. And then if c equals n, return false. In this case, we need to backtrack. So now we can implement like these choices. So just looking at every single column, because we said moving left to right, looking at every column, top to bottom. For I in range n, we need to say if the move is valid, if is valid move, and we'll pass in the board, the r, and the current column. Then we will set the board to queen, and then we'll move on to the next row because we decided if we do place it, we'll move to the next row. So we'll solve r plus 1, 0, and then if this does turn, if this is true, then we will append the solution to, so like if we get r equals n, we've placed n queens, we will append this solution to our ret array. So we'll say ret.append copy.deep copy. And the reason for this is that lists are passed by reference. So if we appended the list, it would keep being changed as we kept like backtracking through and finding all of the possible solutions in this method. So we want to create a deep copy and append that deep copy to our array of our current board. And then after doing this, we want to set all the things we set to queue back to period so that we can essentially backtrack. So in the case that solve evaluates to false, we'll backtrack, and then after we do solve, we'll like be in this part of this, we'll be in like a certain function on the stack that has this evaluates to true, but then we'll set the solving step back to period so we can begin to backtrack and find all possible like distinct solutions of the n queens puzzle. So now it looks like all we need to implement is this is valid move. And right now I'll keep to implementing this as a closure, which is just like a function inside like the first class function. So what we need for this, it's actually a little complicated because searching diagonally isn't something that's like super, I don't know, it doesn't make that much sense. But what we could do, I guess like my crazy idea, rather than having like a while statement in each of the 8 directions, because a queen can attack 8 directionally, is that we can just loop over the different unit changes, like that would be up, down, left, right, moving up into the right, down into the left, up into the left, down into the right. And then, while we're not at the end of the board, keep moving in that direction. So we need a direction array, and this will have, is that down, up, or I guess like up, down, left, right, and then now we need the diagonal moves, which is like up into the right, down into the left, up and to the left, and down and to the right. That looks, yep, and that looks good. So that should be all 8 directions that a queen can move in. So now what we're going to do is we're going to say for dr, so like change in row, dc in direction, I'll call this directions. Our current row and current column is equal to r plus dr, and our current column is equal to c plus dc. And then we'll say while 0 is less than or equal to current row is less than n, and 0 is less than or equal to current column, which is less than n. We will see if the current row and current column is q. So if board at current row, current column equals q, return false. Else we would move we keep moving in that change in direction. So we say current r, current c equals current r plus dr, current c plus dc. And then if we get to the end and we see no problems, return true. Cool. So, I mean, given that this works, this should actually work. So we're just going to be going, like we set up here, moving left to right, top to bottom. If a move is valid, we're going to place it, and then we're going to try to solve the next row. If it's not valid, we're going to try the next column until we get to the end. If we get to the end and we don't solve it, we'll return false, try an earlier row. And then if we do get to the end, if we've placed n queens, so if r equals n, so we get to a row that is the length of the board, then we'll just append this board to our red array, and then we will return the board at the end. So let's see. Okay, C is not defined. Do you mean DC? Oh, so I actually said I, but I want this to be column, so I'm going to change this to C. Cool, that worked, and nice, that worked. So let me know if you guys have any questions. I think this is a really great backtracking problem. Like this and Sudoku Solver, like the 2 best backtracking examples that I know. So yeah, if you have any questions about it, just put them in the comments down below. And have a good one. Talk to y'all soon. Peace.